Bell Labs was a researcher's nirvana. I joined this fledgling group called the Computing Science Research Center. This collection of people ended up having a profound impact on the field of computer science.
Computing is a worldwide fellowship. I think you were referring to Unix.
Unix was really created as an educational vehicle. There was no security in the first versions of Unix. The open source software community on the outside has really focused on Unix for their open source offerings. Linux and the GNU compiler collection, these are some of the premier open source software systems.
You were involved in some of the early research in the core of computer science, the foundations, the kind of things that are now in textbooks. What are the next frontiers?
Computer science is poised to have even more impact on the world at large than it has up to this point. What kinds of algorithms and data structures does the human brain use to process information? We're making enormous progress in applying computer science ideas, computer science algorithms to areas like genomics, doing sequence alignment. I think these kinds of questions become approachable through the use of algorithms, computer science techniques, data mining techniques, but most importantly, it's going to be a collaboration with biologists. Today, there's a multi-billion-dollar industry that's involved in building tools for constructing classical computers. There is a new style of quantum computing that's being investigated called topological quantum computing. Programming the topological quantum computers becomes a job for topology. We're computing braids in space-time.
I know you grew up in Canada and then you went for undergraduate studies to Toronto. I suppose at that time there was no computer science department. What were your interests at the time and what did you study?
I took engineering physics at the University of Toronto. In the engineering physics program, we got the courses of the math majors, the courses of the physics majors, and then they made up some special engineering courses for us to take. But I really enjoyed the math courses, and you're absolutely right, there was no computer science at the time. I think the University of Toronto had gotten their first 650 IBM computer, so computers were just starting to come on stream. But I really became interested in computer science when I did my senior thesis. I discovered Boolean functions, and I was particularly intrigued with minimizing Boolean functions. So I read as many papers as I could on this subject. I discovered that half the papers were co-authored by a researcher by the name of Ed McCluskey, who was at Princeton at the time. So when I finished my program at the University of Toronto, I thought of graduate school. I had heard of two universities. I wasn't very knowledgeable about graduate study in computer science at that time, but I heard that MIT had some interest in computers, and then Ed McCluskey was at Princeton. So I almost went to MIT, but Ed McCluskey kept writing me these very personal letters saying, why don't I come to Princeton, study with him, and then we could clean up the field of minimizing Boolean functions. So after a while, all I got were forms from MIT, but I got personal letters from McCluskey, so I said, I think I'll go to Princeton and study with this great man. Shortly after I get to Princeton, however, Stanford hires Ed McCluskey, but then Princeton did the best thing. They hired a young assistant professor by the name of John Hopcroft, and he inherited both of McCluskey's students. He Hopcroft, however, had only one research problem at the time, and fortunately he gave it to the other student, and it took over 35 years for the research community to solve that.
What problem was that?
That was the problem of equivalence of deterministic pushdown automata. And as you're well aware, maybe in the last 10 years, this was solved by some Indian scientists. And it was a celebrated open problem at the time I started off at Princeton, but very little progress had been made on it.
So you were lucky. He had already given it out. Yeah.
Well, I had a very interesting experience in my third year. I had met Jeff Ullman in the registration line for the PhD program at Princeton. When I was at Toronto, I didn't really find very many bright people, but when I came to Princeton, I met Jeff Ullman in the registration line, and then I met John Hopcroft, and I said, I must be on a different planet because they don't make people like this at Toronto. Since I didn't get a ready-made research problem from Hopcroft, Hopcroft said, you find your own research problem. And I spent the first 6 to 9 months of my third year tearing my hair out looking for a suitable topic on which to do a PhD thesis. Now, at that time, I was very interested in some of the work that Don Knuth had done on LR parsing, and I was also very interested in some of the work that Noam Chomsky was doing on formal grammars for languages. And I thought this would be a very interesting area to look into more deeply. And as you're well aware, Chomsky had this hierarchy of languages and grammars. And I, for my thesis, said, can we find a class of languages between the context-free and the context-sensitive that would have the same kinds of properties that the context-free languages have, but languages that would be, or grammars that would be able to describe more of the syntactic constructs that are found in programming languages. So I created this new family of grammars called index grammars, and also found that there was a natural class of automata that would recognize the same family of languages as the grammars, very much the same way as there are context-free grammars and pushdown automata, that there are two different ways of defining the same family of languages. So this, in many ways, started off my interest in grammars, languages, parsing technology, and interest in compilers and programming languages.
Besides you and Jeff Ullman, and I guess John Hopcroft in the faculty, how big was the computer science group at the time in Princeton? How many people, students or faculty, were actually doing that?
Well, this was very small. In fact, Ed McCluskey was in charge of the computer science program. This was a program within the electrical engineering department. So to study computer science at Princeton, you first had to become a student in the electrical engineering department. And there were just 2 or 3 faculty members that were part of the computer science program. The other programs in the graduate programs in the electrical engineering department were solid-state physics and communications theory. They had been much more mature and had more people in them, but computer science was very much of a fledgling area at Princeton. So as a consequence, my graduate education really consisted of taking 10 math courses from the math department at Princeton, and then Hopcroft had a special computer science course that covered the computer science field. The rest of the courses were in, I took some in communication theory, and also at that time at Princeton, you had to select 3 areas for your qualifying examinations, and you had a choice of mathematics, communication theory, solid-state physics, and computer science. So I chose computer science to major in and take minor exams in mathematics and in communication theory. I particularly remember the mathematics exam. They would send over two professors from the Princeton mathematics department. The professors from the math department would ask the questions of the candidate, and then you'd be graded by the electrical engineering faculty on your answers. And these were very stressful times because the first question that the math professors asked me were, "What math courses have you taken?" So I had a big smile on my face and rattled off the 10 math courses I had taken at Princeton. And the professors started smiling more and more as I recited this list of courses. And then all of a sudden I realized what a hole I was digging myself into, because then they felt they could ask me questions in any one of those areas. So the first math course that I took at Princeton was from Alonzo Church.
Oh, so he was still active there teaching, yeah.
He was teaching. He had been there for quite a while, but he, as you're well aware, was a grand old man of logic, and he had defined lambda calculus. He was working on his book on mathematical logic at the time. His book was very interesting from the perspective that there was almost more text in the footnotes than in the body of the book. And most of his lectures were actually spent gossiping about the great logicians of the 30s. But he was a brilliant man, and I got a perspective from him on the personalities in the field of logic, perhaps more so than getting a very deep insight into mathematical logic, which I had to learn on my own.
Did he have contacts with the the computer science group in the electrical engineering department? And how did he view the developments in the computer field?
I think he was pretty aloof from the electrical engineering department, but the mathematics department at Princeton had a reputation of having graduate students who became pioneers in the field of computer science. People like Michael Rabin, John McCarthy, and many others. And so Princeton was extremely influential in launching the field of computer science. The electrical engineering really didn't know what to do with computer science at the time, and you, I'm sure, are familiar with some of the notorious battles they had between the more traditional areas of electrical engineering and the new computer science department. But computer science at Princeton ultimately grew to become one of the great departments in the nation, as I'm sure you're well aware.
Yes. After you finished in your studies at Princeton, I know you went to Bell Labs afterwards, but what were your thoughts on your career?
Well, at that time, there weren't very many computer science departments. In fact, there were probably only a handful. And for the people who were interested in continuing in computer science, like Jeff Ullman and myself, the choice was really going to an industrial research lab. And the premier industrial research lab at that time was Bell Labs. Ed McCluskey had had some connections with Bell Labs. Jeff Ullman had just graduated a few months before I did, and he had gone to Bell Labs. And John Hopcroft had spent some time at Bell Labs. So Bell Labs, I thought, was a natural place to continue my research career. And at that time, Bell Labs was a researcher's nirvana. I joined this fledgling group called the Computing Science Research Center. There were only a handful of us in there, but this collection of people ended up having a profound impact on the field of computer science and on the whole industry of computer science. This is the lab that invented Unix and C. Many of the commands that are on Unix came out of a marriage between theory and practice. There was a world-class mathematics research center, and of course Bell Labs is renowned for its research in physics. So what I really liked about Bell Labs was that you were surrounded by brilliant people from a variety of disciplines. If you ever had a question about mathematics or physics, you could go to the world expert in that area and get an answer instantly. It was also a very problem-rich environment. People were thinking about all sorts of new areas, new things to work on, and sometimes if you had a perspective or an idea on how to attack a problem that some of the other researchers didn't, it led to a wonderful opportunity to do some collaboration. In fact, in the first few years of my career at Bell Labs, I ended up writing more joint papers than singly authored papers because there were so many interesting problems. Many of the papers that I wrote initially were done with Jeff Ullman, and we were working in the area of formal languages and automata theory at that time. But since Unix was being developed, I discovered that I could write papers much more readily with the Unix tools than doing them in the traditional way of writing them out longhand, then giving them to a secretary to type out, and then doing proofreading and so on. It was much easier to be able to enter the text directly into the computer. And there was a lot of interest in turning Unix into a good platform for producing scientific publications. Doug McElroy, who was my boss, was very interested in both good writing and in tools to facilitate good writing. So in fact, he taught me how to write. He had taken a course from Strunk when he was an undergraduate at Cornell. And when I first arrived at Bell Labs, I really didn't know how to write. But he made me very conscious initially of good writing. And over a period of time, I had written a number of books. And when you are your own copy editor, all of a sudden you discover that there are certain practices that you need in order to communicate effectively. So the writing of the books was also a very interesting part of my career at Bell Labs because I was teaching at Stevens out of hours because I found both doing research, teaching, and writing to be very synergistic. And working on the books was also very useful at that time because it allowed me to codify the little knowledge that was known about many areas of computer science.
Yeah, that was the early days of computer science, of course, where books in many of the areas that were being developed did not exist. Did Bell Labs encourage the writing of the books or tolerate?
No, I think, in fact, it encouraged them. The president of Bell Labs at that time was a person by the name of Bill Baker, and he heard that I was writing a book on algorithms. And whenever he saw me in the hallway, he would always encourage me and say, Al, one day algorithms are going to be very important. Keep working on this subject. And when he heard that I was writing a book on algorithms, he actually got me to give a videotaped course at Homedale on what I was writing in the book. And I thought it was very prescient of him to, first of all, say that algorithms was going to be a very important area for the future, and also to encourage all the other people at Bell Labs to take an interest in algorithms. And for almost a decade after I taught this videotaped course, there would be many engineers and scientists at Bell Labs who would meet me in the hallway and say, "That was a great course you taught." And I said, "What?" And I said, "How did you know about the course?" I said, "Oh, I took your videotaped course." So what impressed me about the management in Bell Labs research was that they were very forward-looking, very willing to encourage activities that they thought would have an impact for the future. And I think, as you're well aware since you were at Bell Labs, the enlightened part of management and their outlook on what constituted research, I think, was also instrumental in making Bell Labs such a nice place to work and such an effective research organization in the field.
So when you joined, the Computing Science Research Center was quite small, right? And did it grow rapidly? You were hiring a lot of people, and was that seen as an important component of a telecommunications company like AT&T at the time?
Well, this is a great question because when I first joined the Computing Science Research Center, there were only a handful of people in the center. Ken Thompson, the creator of Unix, had just been hired. Dennis Ritchie came on stream roughly at the same time. Jeff Ullman was there. And there was an attitude that the telephone companies needed a good platform for running their operation support systems, and that they needed an operating system that could be then used to run these operation support systems. So Bell Labs had gotten into an agreement with MIT and GE at that time to create an operating system called Multics. And this was a grandiose operating system from the perspective that it was very ambitious in its goals and capabilities. But after several years of working on the system, it did not get completed, and eventually Bell Labs management got tired of waiting for this super operating system to be developed, so Bell Labs dropped out of the Multics project. Ken Thompson had been working on the Multics project, and when it stopped, he discovered a cast-off PDP computer in the attic and said, "I think I know how to create an operating system that has almost the same capabilities, but with much less software." So that's how the first version of Unix was born. And then several other people decided to take an interest in the operating system that he was working on. In particular, Dennis Ritchie joined him early on. And the third version of Unix, Dennis Ritchie created a special purpose language, a systems language, that got to be known as C. And the third version of Unix was implemented in C. So it turns out today, Unix and its derivatives, like Linux, are the predominant operating systems on the servers that are on the internet. And C is one of the most widely used systems programming languages in the world, even now. And if we also look at the derivatives of C, languages like C++, which was developed by Bjarne Stroustrup, who was also in the Computing Science Research Center a little later, and C#, Objective-C, which is used by Apple. The work that was done in the systems area at Bell Labs at that time had a really profound impact on the industry. What I liked about Unix, in addition to being able to write papers on it, theoretical papers, was that it gave me an opportunity to experiment with some of the algorithms that I was working on, particularly for string pattern matching problems. There was also a remarkable collaboration that I developed with one of the other researchers who had joined the Computing Science Research Center, namely Steve Johnson. Now, Steve Johnson did his PhD in category theory at Columbia.
Very theoretical,
Very
very
theoretical.
mathematical. Yeah.
And I think he got a little tired of abstraction. So he came and joined the Computing Science Research Center he wanted to write some programs. But my first encounter with Steve Johnson was perhaps indicative of some of the unusual kinds of researchers that were at Bell Labs. He came into my office waving a book. I had never met him before, never seen him before, but he comes into my office and he's waving this book entitled Recursiveness. It was written by Elgot and Eilenberg, his advisor at Columbia. And instead of saying hello or anything of this nature to me, he says, I understand you know what the theorems in this book mean, but you don't understand the notation. I understand the notation, but I don't know what the theorems mean. Shall we read this book together? And out of that initial conversation came one of the most significant tools for impacting the construction of parsers for programming language compilers. Steve Johnson was interested in moving Dennis Ritchie's C compiler to another machine, and he was having a little bit of difficulty understanding the parsing mechanism. Since I had studied Knuth's LRK parsing algorithm, and people were then very interested in trying to make it more efficient for practical use, we had a number of ideas of how we could harness it in the context of a practical tool generator. But my initial foray into helping Steve Johnson was to construct the parsing tables by hand on a big sheet of cardboard. And I would do it over the weekend, watching television, and then on Monday morning I'd bring in the big sheet of cardboard and give it to Steve Johnson and say, okay, here's your parser. Then he'd proceed to implement it. And of course it didn't work correctly because I'd made some mistakes. And then I'd repeat the process of correcting the mistakes the next weekend, and again bringing the sheet of cardboard to him, and he'd correct it, and it still wouldn't work. Finally, he got so frustrated, he says, tell me what you're doing. So I explained to him the LR parsing algorithm that I was using, and he went off and implemented it, and this is how YAC became born. And one of the things that I had not appreciated at the time was how much leverage programming languages could give to different application areas, and if one could construct compilers for programming languages with much less effort, then we could create many more languages for special application areas. One of the first users of YAC was another Princeton graduate who had joined the Computing Science Research Center by the name of Brian Kernighan. And Kernighan had been working with Dennis Ritchie on writing the C programming language book, and he had written a number of tutorials on how to be an effective C programmer. That's where I learned how to write C programs. But Kernighan also had interest in typesetting, and particularly typesetting mathematics. So he had this idea that it would be nice if we created a programming language that allowed people to express mathematics the same way a mathematician would talk about mathematics over the phone to another mathematician. So he and a colleague of his, Lorinda Cherry, developed this little language called EQN that was a very convenient way to specify mathematics in scientific papers. I used it all the time, but another interesting aspect of developing applications using any tool is that sometimes the people using the tool can give you suggestions on how one ought to evolve the theory and how one ought to make the tool better to be able to do a wider class of applications. So some of this early work in use of YAC to create little languages for various areas improved YAC and also allowed us to develop the theory to be able to apply the Knuth's algorithm to ambiguous grammars, for example, so that would make the specification of languages easier for programmers, but we could still produce very efficient parsers using the LR parsing algorithm for them. So Don Knuth had this dictum that the best science is motivated by practice, and the best practice by science. And I'm a big believer in Knuth's dictum that I found the applications of language theory nourished the field of language theory at the time, and language theory could also have a very profound impact on the area of compiler construction.
Compilers is an area where theory has had a big impact. I mean, your work and Don Knuth and have had a real impact. I know you have written papers with Steve Johnson, classical papers on optimizing compilers. It's interesting that many of these creators of these tools were actually yourself, Steve, and so forth, had a good grounding in mathematics also and theoretical thinking. Was that a sign of the time, or was that an important factor in how computer science in this era developed?
I personally think that if you are trained in mathematics, you think in terms of abstractions that are more elegant, easier to prove correct, easier to ultimately implement than if you just try to use ad hoc methods. And I'm still a great believer in the power of appropriate abstractions. One of the most recent areas of interest for me is looking at computational thinking. And the way I like to define computational thinking is that it's inventing the abstractions with which you can solve problems using algorithms and computations. So it's a two-step process. First, you have to develop an appropriate abstraction for the problem area at hand, and then you have to devise the algorithms that can effectively harness that abstraction for solving practical problems. One of the areas that I like to use as an example of computational thinking is the development of quantum mechanics as an abstraction for understanding quantum phenomena, and it has led to the abstraction of quantum circuits, which then can be used to help create algorithms for quantum computers, and also ultimately, I think, will be very instrumental in the design of quantum computer compilers. The former director of the Computer and Information Science and Engineering Directorate at the National Science Foundation a few years ago wrote a paper on computational thinking for everyone. Jeanette Wing felt that computational thinking is as important to the average citizen as reading, writing, and arithmetic in the information age. And so the National Academy commissioned a study group, and we had a bunch of workshops where we looked at how computational thinking was being used in the K through 12 curriculum, and we also speculated on how we could improve education by the use of computational thinking and teaching computational thinking. The reason I mention this is that when we design programming languages are very often designed around some kind of model of computation. So if we take the functional languages of today, languages like Haskell, OCaml, ML, even Lisp, the computational model is really Alonzo Church's lambda calculus, where you use recursive functions as the underlying method of computation. If we take the more classical languages like Fortran and C, the computational model is really the von Neumann architecture. So embedded in programming languages is a model that the designers of the language had in mind of how people ought to think about solving problems using their language. And getting back to your question on use of mathematics, I think one of the traits of mathematics has always been to try to come up with the appropriate model for the problem at hand and have a model that's simple enough to capture the phenomena that you are interested in and no more complicated than it has to be. I think that's a very good algorithm and prescription for designing programming languages as well. And if we look at a language like C, it's really very Spartan in terms of its computational model, but that I think also has given its great flexibility to be applied in a wide variety of application areas. And it also is the reason why it's often used as the prototypical example of the language to use if you want the most efficient program for a given task, because it's got very little overhead involved in how you write the program and implement the algorithm for a given task. So perhaps this is too long of an explanation of why I'm fond of mathematics and why I think it's so important to have the right kinds of models before you develop programming languages or computer systems of any kind.
Now, you have you are the designer of a successful language like awk named AWK. You are the A for the AWK, which is reached, has been used in extensively. Is that some of the thoughts that went in designing the language, and was that what were you trying to do, and what were your methods, and how do you feel about its impact?
In the early days of designing awk, Brian Kernighan had been interested in programmable editors. Weinberger was interested in solving a number of routine data processing problems that come up in everyday life. And I was particularly interested in string pattern matching algorithms at the time. And what I thought would make a very good model of computation for solving these data processing problems is to have a pattern action language. Human beings are stimulus response creatures. If you hear a loud noise, you'll turn your head in the direction of that loud noise, or if you see something, you'll immediately take a look at the unusual scene. So awk was designed in writing programs that consist of sequences of pattern action statements. A pattern specifies the kind of pattern or phenomenon you're interested in, and then if you see that in a text file, you can specify an action that you should take. Just taking a very simple example of this, if you have a file that has names and phone numbers, a very simple way of finding the phone number for a given person is to specify a pattern, say name matches Mahalis, and then the action is print phone number. Now you're an awk programmer. It's just a one-line statement, and you can read a file of name and phone numbers, and you'll immediately get the answers that you want. I just recently got a book from a German biologist who has been very fond of using awk to study problems in genetics. He has huge files, and he's using awk programs to look for patterns in DNA sequences. He said the reason he's using awk was because it was so easy to learn and so effective for solving the kinds of problems that he was interested in. One of my early awk stories is when awk came on stream, because it was so easy to write common data processing applications in it, people started using it all over the place. And I was surprised at how many different kinds of applications people were implementing in awk. I didn't think anyone would write an awk program that would have more than 5 or 6 statements in it. But one Monday morning I came into Bell Labs, and there was somebody from the microelectronics division of Bell Labs who was sitting in my office, and he said to me, I've written this 10,000-line awk program to do circuit design. And I just about fell off my chair because I didn't expect anybody would write even a 10-line awk program, let alone a 10,000-line awk program. But what he said was that it allowed him to solve problems in 2 months that would have otherwise taken him 2 years. So it turned out to be a very useful tool in a broad range of applications. And often what has been said is that if you do many more things with a screwdriver than turn screws. So if you create an easy-to-use tool, chances are it will be used in many different application areas that the tool designer didn't have any idea of.
While you were at Bell Labs, how was the relationship with people outside the research community? And did you have contacts like that often while there? And did you find that your research could connect well with the development side of the company?
Again, I think that's a very good question. It also shows the beauty of Bell Labs at that time. The research area and researchers in the research area were expected to act as consultants for engineers in other parts of the company. And I remember very fondly giving a talk on algorithm design techniques. This was when I was working on the Design and Analysis of Computer Algorithms book with John Hopcroft and Jeff Ullman. And at the end of my seminar, this young woman from the Technical Information Libraries at Bell Labs came up to me and said, "Can you help me? I've written a bibliographic search program that is taking too much time." So she described this program that she had written and how some gung-ho bibliographer had written a search that had over 100 keywords and phrases in it. And at that time, the search was being done over a magnetic tape that Bell Labs got from Washington. It was a magnetic tape that had the current technical papers and reports that had been written under government contracts. But this particular search that was giving her problems had cost $600, and it had not yet found all of the bibliographic items satisfying the searcher's prescription. There was a $600 limit on how much money you could spend on a search. So I asked her how was she doing the search. So she said, she reads a buffer full of bibliographic data from the tape into the computer, then looks for the first keyword, the next keyword, and so on, and then repeats the process. So since I was writing this chapter, I said, oh, why don't you, instead of looking for the keywords one at a time, construct a pattern matching machine that will look for the keywords in parallel. So you can read a buffer full of tape and then search for all of the patterns in one pass over that buffer and do the same thing. And by the way, here is a very efficient way of constructing that parallel pattern matching automaton. So a few weeks later, she comes back into my office and said, remember that algorithm you suggested to me? I implemented it, and now that $600 run costs $25.
This interplay between theory and application, was that something characteristic of Bell Labs or computer science in general in the early days?
Well, my heroes in computer science were people like Alan Turing, Don Knuth, von Neumann, people who were towering scientists, but also had an ability to see how the science could be applied to practical problems. So Turing, perhaps the father of computer science, is very well known for his work on decryption during World War II on the German Enigma machine. Don Knuth was very interested in making books, especially books containing mathematics, beautiful. So he took several years out of his career to develop a mathematical typesetting system called TeX that's widely used by many people in science to typeset their technical papers. I might mention that Knuth used the notation that Brian Kernighan and Lorinda Cherry developed for the EQN language and incorporated that into TeX because he found that a very elegant way of specifying mathematics. So Knuth is perhaps most famous for being the father of the area of algorithms, and his Art of Computer Programming series was sort of the Bible for many of the people, particularly in the early days of computer science. I certainly spent many a pleasant evening reading it. And then von Neumann, of course, was one of the people very instrumental in building one of the first stored program computers at the Institute for Advanced Study. So it takes a very unusual individual who has the ability to advance the field from a theoretical basis, but who also is respected well enough to be able to make practical contributions. So I've admired these kinds of people and this kind of contribution. And this also seemed to be a very nice kind of centering force for the researchers at Bell Labs, that you weren't expected to just go into your office and close the door and write papers, but you were expected to interact with other researchers and with people in the rest of the company. And I think that had a lot to say of why Bell Labs Bell Labs research for many decades was the world's foremost industrial research lab, because it had this enlightened view of giving researchers the freedom to pursue their research interests, but yet having an expectation that the research should ultimately pay off, but not necessarily in 6 months' time or 12 months' time, but they could take a much longer range view of doing research.
So you spent several, maybe a decade or more in management, at different levels of management at Bell Labs. How easy was it to do that? How enjoyable was it? And How did you find this uh, facilitating of contacts of research and the more product side of the labs? How smooth was that?
This question and issue could take many days, maybe months to discuss, because technology transfer is a complicated process. One of the most successful technology transfers that I was engaged in was the head of the Unix Systems Laboratories. Actually, he and I play bridge together. This is Bob Martin. Was noticing that a number of software developers, both within research and in some of the advanced development areas of Bell Labs, were using Bjarne Stroustrup's C++ language. And were saying very good things about how it facilitated software development, reduced cost, reduced errors. So he asked me, did I think C++ was ready for commercialization? And I said, well, I too have noticed that there are many people in the development areas using it successfully. I think so. So out of that casual conversation, the next thing I discover is my management said, Al, commercialize C++. And dealing with Unix software laboratories at that time, they really didn't understand object-oriented programming languages or how to develop software in object-oriented ways. They also didn't understand how to manage researchers, especially the kinds of researchers that we had at Bell Labs. I had some of the most tumultuous meetings with management in the business unit, trying to protect Bjarne Stroustrup from how the business unit thought researchers should be managed. They thought that they should be able to tell Bjarne Stroustrup how to design the language and what changes to make in the language, when they really didn't have any background or experience. But that was sort of the nature of a business unit. They thought they knew the market. They thought they should be able to design how the product goes. But I've noticed that the most successful products in software are systems that grow and evolve on the basis of user needs. And so Bjarne was very much of the school saying, let's evolve the language on the basis of how people want the language to evolve, rather than how some MBA or business manager thinks the language ought to evolve without having an experience in doing this. So the hardest part of the job was trying to educate the people in the business unit about the culture, and especially the emerging culture in the software industry. If we look at the giants in the software industry today, if we take, say, the late Steve Jobs as an example, he was acutely aware that you should design products that are easy to use and meet user needs, a very different kind of mentality from what used to exist in business units. So I found that the toughest part of doing technology transfer into the business units, basically setting the expectations of the business unit managers to match those of what constituted an effective interaction with researchers. The best technology transfer, though, often occurs when researchers work side by side with people in the development areas, and we had a number of good examples of this taking place in certain areas with the Bell Labs development areas, particularly in the area of fiber optics. There was a very close connection between the researchers in fiber optics and the people who were developing the fiber optics products. We also had a strong influence in trying to teach software developers good programming practices and issues about how to do testing and how to try to put in place processes that lead to more efficient and more robust software development. But because of the nature of the business and many of the software systems that were developed by Bell Labs at the time were huge. They were often in the millions of lines of code, sometimes in the tens of millions of lines of code. It was very difficult to retrofit new technology to an existing development. And so the most successful transfers were where some pioneering group would try out some of the new research technology in anticipation of the next product, and then being able to incorporate the research advances into the next generation development. Certainly if we look at the spread of Unix and C into the development areas, that was the way it occurred. People didn't take an existing system and rewrite it using Unix and C. They developed the next generation systems using Unix and C. But senior management at Bell Labs was often quoted as saying, technology transfer is a contact sport, and as with any contact sport, it can sometimes be bruising on both sides.
How much interaction was between computer science and other parts of Bell Labs, mathematics, physics, other parts of research?
The Computing Science Research Center was born from the Math Center. Many of the initial people, like Doug McElroy, were in the Math Center. The first director of the Computing Science Research Center, Sam Morgan, was a mathematical physicist who came from the Math Center. So we had very intimate connections in the beginning, and even as time went by, there was a great deal of interaction between people in the Computing Science Research Center and the Mathematics Research Center. Ron Graham was the director for many years, and many of the particularly more algorithms-oriented and theoretically-oriented computer science people in the Computing Science Research Center would collaborate and work with the people in Ron Graham's research center. And I remember one very interesting anecdote of the quickest paper I wrote occurred because I was sitting in a seminar next to Neil Sloan, who was in the Mathematics Research Center. He had written the book, Handbook of Integer Sequences. I was looking at the performance of a parsing algorithm. I had reduced it to a recurrence relation. I guess he thought the seminar that I was in with him was also dull because he kept looking at what I was doing on the sheet of paper. And in the middle of the seminar, all of a sudden he yanks out the sheet of paper from under my pencil and in a loud voice says, "Where did you get this?" And it was the performance of a parsing algorithm. But what was interesting about it was that since he liked to be comprehensive, it was a recurrence that wasn't in his handbook. So he immediately wanted to rectify this. But by 2 o'clock that afternoon, we had reduced this recurrence to a very simple form. By 4 o'clock, we had shown the solutions were of this generic form, and then by 5 o'clock, we had written the paper. The only thing that Neil wanted to do afterwards was to go to the Brown Library and check to make sure that he had the references correct. And some of the references were from places like Principia Mathematica, and that was the only thing that prevented the paper from being immediately sent off to the journal that day. But from 11 a.m. to 5 p.m., I thought was a new record for creating a paper which was published in the Fibonacci Quarterly and was also included as a exercise in Don Knuth's handbook, The Art of Computer Programming. There are anecdotes of this nature, but they're like the Shen Lin was in the Mass Center, and the Lin Kernighan heuristics for graph partitioning and the traveling salesman problem were result of serendipitous work between computing science research and the Mass Center. So I think the relationship was almost the organizational boundaries between the Math Research Center and the Computing Science Research Center were almost invisible. There were some interactions with people in the physics areas, but because the distance between computer science and physics from a field point of view, a science point of view, was further, and also they were in a different building. They weren't nearly as frequent or as intense.
Was it compartmentalized? Here is computer science, different building,
No,
math, different physics.
although there tended to be concentrations of mathematicians and in certain corridors. Interspersed amongst these would often be people from computer science and vice versa. So physical proximity meant a great deal towards fostering collaboration.
As a manager, when you were you wanted to make the case for, the your research group is doing great work, let's hire more, or let's support them. How easy was that to do within the the industrial environment? How much do you have to argue? How did you have to argue that this contributes to the company and this is good for the company? And how easy was it to make that argument?
In the heyday of research at Bell Labs, it was always a good practice to make sure that your management chain was aware of the significant work that was being done in your organization. So when I was heading a department head in the Computing Science Research Center, I made sure that my fellow department heads and the director of the center were well aware of the work that was being done in my department. When I became the director of the Computing Science Research Center, I made sure that the vice president who was in charge of research and the president of Bell Labs was well aware of some of the impact that we were having on the company and also on science. Part of the purpose of Bell Labs research was also to maintain a presence in the scientific community so that we would continue to be a magnet to attract some of the best and brightest young researchers to Bell Labs. So if you did your job as a manager, you could always make the case for hiring somebody who you wanted and who would fit into the organization. Now, occasionally there were times, because of headcount constraints, that you'd have to either do special pleading, but the times I was involved in management, there was a consensus that if a target of opportunity arose that was in an area important to the company would find some way of hiring that person. I don't think that is the case today at Bell Labs, and also may not be the case at industrial research in general, because when Bell Labs research was at its greatest, AT&T was a monopoly, and so it had a stable and secure source of funding. So funding is always a crucial issue for any research organization. And once AT&T was broken up, more competition came to both Lucent when it was spun out of AT&T, and to even AT&T itself because of the regional Bell operating companies being split from AT&T. So the funding wasn't as stable as it used to be, and then one was subject more to the vagaries of the fortunes of the company in terms of how easy it was to make cases for hiring new people. But another characteristic of management at Bell Labs was that the people who ended up being managers were people who had been scientists. And frequently, when somebody was asked to go into management, they didn't want to do it because they were having too much fun being a researcher. So usually these people had to be persuaded to accept these management positions. But I've always thought it was a very good idea for scientists to manage scientists because they have the centering forces of what it takes to have a productive organization and what kind of people one ought to be hiring.
How things have changed for industrial research in computer science in general, or have they changed? In other words, at the time, Bell Labs, IBM were very, Xerox PARC, and had a active research, very research endeavors in computer science and other fields. And now, of course, less so at Bell Labs, but have the new giants of the industry, Microsoft, Google, do they play the same role that was played by AT&T at the time? And has anything changed in the character of industrial research?
That's a very interesting and profound question that I look at the students that we graduate from Columbia and those who want to pursue research careers. Certain industrial research labs are at the top of their lists of where they'd like to be able to get jobs. So Microsoft Research has a lot of very talented researchers. They're very selective in terms of who they hire, but I think it's still a very good industrial research lab. IBM Research has for decades been a very strong industrial research lab, and again, it's I think a very good place for researchers to flourish and to develop their careers. Google tends to mix its engineers and researchers together, although it has a organization that it calls research, but it's not the kind of research lab that used to exist at Bell Labs. But they've been a significant force in development of innovative software systems. And so from that perspective, I think they've been very influential in the industry. And I just saw this morning that they've announced a new product where you have an eyeglass that connects you to the internet. So they are very innovative in terms of the kinds of products that they're thinking about for the future. And they also have some very talented people. Speaking of talented people, one of the things I should mention is that at Bell Labs, we had summer interns, and some of the summer interns were really fabulous, turned into fabulous researchers and scientists. One summer I had Eric Schmidt, who was the CEO of Google, as a summer intern, and he was just a fantastic summer intern. He had taken some of the regular expression pattern matching algorithms that I had developed and put them into the second version of LEX, this program that Michael Lesk had developed to create lexical analyzer. And he did the whole job over the summer, understood the sophisticated algorithm, packaged it up in a Unix utility that's essentially part of Linux today. I also had Gene Myers, who worked with Celera as their chief scientists, doing research into string pattern matching algorithms, techniques that he applied when he was at Celera. So Bell Labs always not only attracted some of the very best graduates, but they also had people as summer interns that were contributed greatly to the field. I think the volume of work that's being done maybe isn't as great in the pure research areas today as it used to be, but I don't have any statistics on that.
You said in another time that computing is a worldwide fellowship. I think you were referring to Unix, maybe at the time. Can you elaborate on that?
Yeah, so that's a very interesting attribute. When Unix was initially created, it was really created as an educational vehicle. There was no security in the first versions of Unix. And the whole reason for this was that researchers were allowed to look at other researchers' code, learn from the other researchers' code, make contributions to every aspect of the system. And you may have heard of Don Knuth talking about literate programming. And Don was advocating, why don't we have a great literature of great software, the way we have great literature in Shakespeare and other areas. So he was very much of the school that you should be able to learn how to write good programs by studying programs written by great programmers. And there was a certain amount of this kind of spirit in the early days of Unix, that you could learn a lot by reading other people's code, talking to the people who had created, and as Unix spread, some of this continued. As you know, Unix spread to academia through the Berkeley software distribution in large part, and became widely used in university circles. I think part of this was due to the ease with which you could add programs to Unix, the ease with which you could get Unix. Then, as the technical community matured, some of the early openness of Unix came back to bite Unix and C in particular, in the sense that hackers, because of the openness of the system, could understand how to breach the security, or whatever little security there was in Unix and C. And a lot of the recent efforts on the part of the security community have been to try to redress some of the openness that existed in the early versions of Unix. What's also, I think, very interesting looking at Unix and C is that the open source software community on the outside has really focused on Unix for their open source offerings. Linux and the GNU compiler collection, these are some of the premier open source software systems that were initially offered to the rest of the world. Now, of course, there's a lot of open source software, but there is a feeling that the community as a whole benefits by certain kinds of sharing. Now, of course, you have to then worry about the protection of intellectual property, software licensing, and so on. And I think the story is still unfolding on this, of how is intellectual property in the form of software going to be protected in the future. If we look at the worldwide community, certainly the Internet, and I think Unix was one of the key components in the creation of Unix, in the creation of the Internet, because of the servers and also the facility with which you could create interfaces to protocols and networks that developed on it. So the Internet, as we know it today, is a great community organization and brings together people all over the world. It's a unfinished story. It's still an unfolding story as to how far we're going to carry and spread the computer science and information technology parts of the industry to all parts of human endeavor and to all parts of the world. But if you combine this with cell phones and smartphones, the world has developed its own nervous system that connects the cells of the world, the human beings of the world, together into one giant fellowship.
At the time when Unix and C were developed, was there a debate within the creators and the company of commercialization versus giving it away free? In other words, for example, the Windows operating system was big deal for Microsoft. Unix is in some ways, was before that quite successful. Was there a debate within AT&T whether to go commercial or not?
I'm not the right person to answer this authoritatively, but in the early days of Unix, there were lawsuits involved between AT&T and the University of California at Berkeley with regard to some of the intellectual property issues associated with Unix and the Berkeley software distribution. AT&T tried to protect the Unix brand name. In fact, we were advised by the lawyers to, whenever we couldn't use the term Unix per se, it had to be the Unix brand operating system, much the same kinds of issues that have occurred with Kleenex and maybe now with Google. But these lawsuits were settled, and when AT&T decided to get out of the Unix software business, it sold Unix to the Santa Cruz operation. So that took Unix outside of the orbit of AT&T, and Unix has developed a life of its own, and Linux has developed a life of its own, and there's a whole industry associated with people who will provide support for Linux systems on the outside. So this is a huge business these days.
After Bell Labs, you went to Bellcore for a few years. How was that different, the environment from Bell Labs?
So I had this life plan that I formulated a long time ago, that I wanted to spend the last third of my career in academia, teaching and working with students.
Oh, you had already decided before?
Yes.
Oh, I see. That's interesting.
When I got the opportunity to go to Bellcore, this was to manage their Information Sciences and Technologies Research Lab. What attracted me to Bellcore was one of the nation's largest software developers. They created operation support systems for the telephone industry. And there was a good friend of mine, Bob Martin, who was in charge of the software business at Belcor. So I wanted to learn how software was really done in industry. So then when I went to Columbia to teach computer science and how software is done, I would have some real experience of how it was done. It was also very interesting to look at how software engineering practices could affect the quality of software. When Bob Martin came to Belcor, Belcor was in the level 1 state of the CMMI, the capability maturity model for measuring the sophistication of software development organizations. And within a few years, he brought them up to level 5. Level 5 is the highest level, and it's called optimizing. In level 1, you have let people do whatever they normally do. And as you move up the levels, you start measuring certain properties about your software. And when you reach level 5, not only do you measure, but you put in places to try to reduce your defect densities and so on. So he had done a spectacular job of transforming Belcor into a really world-class software development organization. So I learned a lot in my years at, I only spent about 5 years at Belcor, and then I went to Columbia. I entered Columbia as department chair. For some reason or another, I thought that I was managing an organization with 300 scientists at Belcor. Managing a computer science department with 25 faculty members would be easy. Turned out to be more difficult than managing the organization of 300 researchers. Academics don't like to be managed. I think they like to have somebody who will lead and work with them to benefit the organization. But this was part of my life plan. I also had an opportunity to see how, particularly at Belcor, how statistics could play a role in both software quality and also in terms of development of search procedures and other procedures associated with software quality. That the statisticians there developed models for how many defects would you find in a software product as a function of time and as a function of how much testing you put in. And so they had these curves, and if they had done the product often enough, that would tell them exactly how many remaining defects there were in a product. And one of the interesting questions is, how many defects would you like to have in your product when you deliver it to the marketplace? When I went to Microsoft for a sabbatical, and I've had a number of interactions with various researchers at Microsoft. About 10 or 15 years ago, Bill Gates had decreed that Microsoft shall produce reliable, secure software, because the initial versions of Windows didn't seem to have those properties, at least as perceived by Microsoft customers. So when Bill Gates speaks, Microsoft listened. So I talked to the vice president in charge of software quality improvement at Microsoft. And it was interesting to see him struggling to try to introduce some of the same kinds of practices that Bob Martin had introduced at Belcor. And maybe I shouldn't mention this, but one of the biggest obstacles to putting in place a tight software engineering process at Microsoft was that Bill Gates was not enamored of software engineering. And the Windows area, in fact, had this cowboy mentality towards the development of software. But as you well realize, changing the culture of an organization is the most difficult job. But I think Microsoft has made enormous strides in improving the quality and the security of their software in the last 5 to 10 years.
Yeah, there's a lot of work on testing and more systematic
Yes.
work on testing, and that's right.
And I think, in fact, if we look at targets of opportunity for research, one of the nice research areas, I think one of the research areas that has a great potential of having impact on software quality is the verification research that's taking place in the computer science research community. People are applying some very sophisticated tools, some of which we had developed at Bell Labs, involving model checking and using formal methods to try to describe properties of software using various kinds of logics to define properties that you'd like to have in your software, and then systematically checking to make sure that every state that your software can get into satisfies those properties. Like there should be no deadlocks. So some of these model checking tools are effective at finding and detecting untoward properties in software systems. When I was at Bellcore, I also talked to a number of the nation's leading vendors in the software business and looked at defect densities in software. It's very difficult to get this information because companies don't publish the defect densities.
Understandably, yeah.
But a few years ago, I wrote a paper for Science magazine. I had been invited to write a paper on software and the future of programming languages. And I began the paper by looking at the question of how much software does the world use to run its affairs? If you take all of the computer systems that are used by companies, universities, individuals, governments, and so on, don't count duplicate systems more than once. Add up the number of source lines of code that have been used to create these systems. How many lines of software does the world depend on today? When I usually ask this question in my programming languages and compilers class, some brave student will say maybe 1 million, 10 million. They don't realize that, say, Windows alone has 60 million lines of software. SAP has over 100 million lines of software in their people management software system. So I just did a guesstimate and estimated that at that time maybe the world used 500 billion lines of software in all its systems. And then this, when I looked at the defect densities that I had experienced, the defect densities seemed to range from 10 defects per million lines of software to 10,000 defects per million lines of software. So if we have 500 billion lines of software with this range of defects, there are an enormous amount of defects lurking in the embedded base. Another question associated with this is, how much does it cost to produce a line of software? And if we just make rough figures, we can easily come up with a figure that's anywhere from, say, $50 to $100 per line of finished and tested software. So if we have 500 billion lines of software at $100 a line, the investment in the embedded base of software is just staggering. What's surprising is that when software works, the highest praise a software developer can get is silence. They don't say anything. But if it breaks, then all hell breaks loose. This issue of correct software is already been important. I have a top 10 list, the Software Hall of Shame. To get onto the top 10 list, you had to have spent $250 million or more and have nothing to show for it afterwards. And unfortunately, it's been all too easy to do this in software. On the top of my list is the air traffic control system that the FAA had commissioned about 10 years ago. And after spending $1 billion, more than $1 billion of taxpayer money, they produced a system that they couldn't get to work. So, and there are commercial companies that have spent hundreds of millions of dollars producing systems that didn't work. Not a good way to develop a career. There is also increasing use of software in embedded systems. So automobiles today and airplanes use hundreds of embedded systems which have software in them. And this software better be reliable, because if it fails, it could produce catastrophic consequences. Control of nuclear power plants. Much of the control is software controlled. Again, these systems have to be ultra reliable. I think this issue of producing ultra reliable software quickly and inexpensively is still a very important open research question, and one that is amenable, and we seem to have evidence to that, for some good theoretical research and good engineering practices. So these are some of the kinds of things that I've been teaching in my courses at Columbia, and some of this experience came from my internship, if you like, at Belcor, giving some real-life verisimilitude to what I say in the classroom.
In terms of your life in academia at Columbia and the practice of doing research, how do you compare that with your life as a researcher in industry?
Being at Columbia is wonderful from the perspective that Columbia is one of the hardest schools to get into. In fact, I think to get into the engineering school at Columbia at the undergraduate level is just as tough as getting into MIT. So the undergraduates that we have at Columbia are just stellar, and working with them is a real treat. We also have some very talented PhD students, as you're well aware. And one of the things I've noticed about being in academia is that you have a much broader spectrum of research areas to choose from. The only downside of this is that before you can do any research, you have to get a research contract so you can pay for your graduate students. So in some sense, you're still limited by who your patrons are. But when I've been at Columbia, I've had graduate students who've done work in such diverse areas as quantum computer compilers, protecting the software runtime from process subversion attacks, to how do you correlate requirements and the code that implements those requirements in a running system, particularly if you're in the programming languages area. The programming language will have an international standard, and if you're creating compilers for that programming language, you need to implement what's in the standard. How do you determine what part of the compiler implements what part of the standard? And my last PhD student did a very ambitious experiment to see if he could automatically read the English requirement and then determine where in the software was that requirement implemented. He didn't solve the problem perfectly, but on the other hand developed three techniques, a combination of which were more powerful and also more capable of detecting where the implementations occurred than anything else that had been done in the research community before that. But this is still a very interesting area of research.
I guess the push is to move also from the English requirements to more formal requirements that are testable.
Yes. There have been attempts at trying to force requirements writers to use more formal methods to describe what the system does. These have been partially successful, but not nearly as successful as they should be. And many requirements, I'd probably say most requirements, are still written largely in English. And as you know, using English to precisely describe anything is very difficult.
You have a great interest in education, and you are involved. You were head of the academic committees at Columbia, and are involved in the university-wide committees to redevelop the curriculum in terms of computer science. What do you see the role of computer science in education in the university, but also before the university in schools K through 12?
This is probably one of the hottest topics of today, of what should we be teaching, especially in the first courses. You may have seen the New York Times article on Maria Klawe, who was a theoretical computer scientist, who was at Princeton, Dean of Engineering, and now is president of Harvey Mudd. And she was on a campaign to try to make the introductory course in computer science be more appealing to women. Frequently, the introductory course in computer science is hardcore programming, and there's often a macho element to that course. Whereas there is a lot more to computer science and to what you do with a computer science education than just writing programs in Java. Computer science is pervading virtually every area of a human endeavor, and the ideas of computer science can be applied to many different disciplines. When I was chairing the academic committee, we revised our curriculum, especially the introductory course sequence. Part of the problem of trying to encourage more students to take computer science, especially, say, getting more women interested in computer science, the problem starts at the high school level, because computer science in high school is not nearly as well developed as mathematics or physics or chemistry. And if one uses AP computer science, which is based in Java, that's not really reflective of what computer science is about and what it can do. So there are efforts to try to change what gets taught in computer science at the high school level. And of course, you realize that introducing anything new into the high school curriculum is virtually impossible, because then you have to give up something. This is where Jeanette Wing, who was advocating trying to teach computational thinking in K through 12, comes to play, because one can teach computational thinking in the context of many other courses. So we could, and in fact, when I was on this National Academies Committee looking at what various people were doing in computational thinking and trying to teach computational thinking, there was one vignette of a grade 1 teacher who had his grade 1 kids dress up as bees. And I didn't know where the pollen sacs on bees were before, but he had the kids be pretty realistic about the anatomy of a bee. And then he'd have some of the kids do this wiggle dance that the bees do to try to instruct the worker bees where the honey is and how to fly to the honey. And if you look at the wiggle dance, it's really a language for communicating information, although the language is dramatically different from any natural language or programming language. In fact, I recently saw an article that there was one mathematics researcher that was using manifolds to try to describe the characteristics of the wiggle dance and how the information was communicated. But that's not for grade 1. But introducing the ideas of here is a mechanism, a language that's being used by the bees to communicate information, and it's a language very different from natural language or programming language, I thought was a very innovative steps. And the kids had a ball dressing up as bees and doing this wiggle dance. The wiggle dance, by the way, is done in the hive where it's dark. So they have unusual ways of communicating the information. This one scientific article said maybe quantum mechanics is involved, but a number of people don't subscribe or believe that. So this is still very much a field in its infancy. If we look at what should be taught, what programming language should be taught in the first course, there has been a great deal of change.
Even in the university now.
Even at the high school level,
Even
but particularly at the university level, I noticed that after many years of teaching the introductory computer science course in Scheme at MIT, they now use Python, a scripting language that's much easier to program in than the Scheme language. And at Columbia, as you're well aware, we're trying to create a new introductory course in computer science that's taken by all engineering students, where all engineering students get exposed to problem-solving techniques using software, using computing. And the problems will be drawn from all engineering disciplines as examples in this first course. This was very much the kind of course that Maria Klawe was espousing for Harvey Mudd to try to get their students to understand the spectrum of applications of computing and how it benefits every discipline. So I think I subscribe to Jeanette Wing's hypothesis that computational thinking is as important as the 3 R's. We still need to evolve what we teach about computational thinking and how do we teach it effectively, because the kinds of techniques that you use in, say, the engineering fields may be, the models are very different from what one might use in other sciences or particularly in the liberal arts. But you can still use computational thinking to analyze texts, analyze scientific data, astronomical data, and as you're well aware, big data is one of the big buzzwords in computer science and in science these days, of how do we mine all of the data that we're collecting, and the data is measured in the petabytes, if not the exabytes or more. How do we find the kinds of patterns that that the data is capable of presenting to us? It can be used anywhere from commercial purposes to discovering how the body works, how the brain works. So this is a very important, very interesting area for future research. And I think it's very important to lay the groundwork for being able to do this research in the first courses, so that students get to see the opportunities, because I think some of the greatest contributions in these areas will come from the students themselves, but they need to be exposed to the problems and exposed to the kinds of techniques that have the potential of being able to make some progress on these problems.
Do you see in the future, let's say in 20 years, do you expect that all students finishing high school will know some rudimentary of the concepts of computer science? And which concepts? Like automata theory that you did as a graduate student, languages or algorithms?
it's virtually impossible to predict 20 years into the future, but I certainly see the trend that algorithmic thinking and computational thinking will become much more widespread in the educational curriculum. Right now, high school kids are very versant at using information technology to play games, to communicate with one another, do tasks of various kinds. But it's one thing to play games, it's another thing to understand what kind of abstractions you want to use, say, to create games, or what kind of abstractions you would like to use, say, to create educational software. There's also a lot of discussion of distance learning, being able to package up courses. Stanford is doing this, MIT is doing this, of being able to offer courses on a worldwide basis. The same courses that get taught to Stanford students, to MIT students, but of course you don't get the interaction with the Stanford professor in the Stanford classroom if you take these courses, but at least the material is there. I think because of the changes to the industry and to where you can find jobs, high school students will realize that being exposed to computer science ideas, computational thinking, information technology ideas will enhance their chances of getting the information technology jobs of the 21st century. So there are forces at play that even without the educational establishment setting up a computer science program in high school will cause some of this algorithmic thinking and some of this knowledge to go into the high school level. But of course it would be really great if we could have a computer science course that was equivalent to Physics 1 at the high school level, so students can get exposed to these ideas early and they would be taught the ideas in a rigorous fashion, the way they're taught physics in a rigorous fashion.
Al, you have been involved in professional societies for a long time, starting with being a chair of SIGACT, the Theoretical Computer Science Organization, many years back. How do you find this as contributing to an impact to the computer science and to society in general?
One of my earliest professional societies that I was involved with was, as you had mentioned, SIGACT, the ACM Special Interest Group on Automata and Computability Theory. And at that time, theoretical computer science was just getting started, but this was an organization that brought together some of the best people in theoretical computer science. When I was chair, Steve Cook, the inventor of NP completeness, was on the executive committee. And so I had a chance to be able to interact with some of the best people in theoretical computer science and keep abreast of what was going on in the field as a whole through my interactions at SIGACT. Over the years, I've also served in various capacities at the National Science Foundation. I've watched the evolution of computer science when computer science was just a part of the mathematics part of the National Science Foundation. Then it became a separate organization within the Mathematical and Physical Sciences Directorate. And somewhat later, it became a directorate in its own right. It's the Computing and Information Science and Engineering Directorate of the National Science Foundation. And part of the reason for doing this also is providing some advocacy for the importance of theoretical computer science in particular and computer science more broadly, saying that it's an important field for the future. We need to be able to stimulate more research, more interest, and more involvement by students in computer science. I chaired the advisory committee for the SCIES Directorate twice, once under Nico Haberman, and then again with Peter Freeman. And as you're well aware, the National Science Foundation funds some of the most talented and most interesting research in the field of computer science. So you're always talking to people who are doing the cutting edge research in the field with your interactions with these organizations. And then most recently, I'm currently chair the Computer Science and Engineering section of the National Academy of Engineering. And again, the company is just magnificent in terms of being able to talk to some of the people who have shaped the field and some of the most talented people in the field. So I guess the reason I like dealing with these organizations is I like the company of intelligent people, and it also allows me to have a perspective on the field so that if I'm department chair or if I'm leading an organization, I can understand where the field is going and where the current trends in the field are. There's no better way to understand what the future of the field is than by talking to the leading researchers in the field, find out what their thoughts are of what their field is doing and what potential it has for advancing the field. So there are many benefits for doing this. The disadvantage is that you spend a lot of time on airplanes or on the train to Washington.
How do you see computer science, let's say, stature developing over the years?
Well, when I started, the first interaction I had with the National Science Foundation was when computer science was still a part of the mathematics division. And I was talking to the associate director for the Mathematical and Physical Sciences Directorate. And he blurted out, I think in a moment of weakness, where he said, he was a chemist. He said, well, we know, of course, that the best programmers are chemists. And I and my colleague on the committee just about fell off our chairs when we heard him say that. But they had a very parochial view of what constituted programming and what constituted computer science. Now that, fortunately, has changed dramatically, and I think the Computer and Information Science and Engineering Directorate of the NSF is viewed as one of the key components of NSF, both on a scientific basis and also as being important to the future of the economy of the United States. There was an interesting anecdote when I was chairing the advisory committee under Nico Haberman. We were involved in a supercomputer competition, and I wanted to learn a little bit more about how software was being written and what kind of quality plan there was for software in the supercomputer centers that were being funded by the National Science Foundation. So I had done some consulting for NASA back in the mid-90s, and I noticed an article in the Washington Post that read, "Global warming isn't as bad as scientists feared because the actual rise in the Earth's oceans wasn't as much as the scientists had predicted." And then they looked at why the scientists had predicted a higher rise in the Earth's oceans was because of a software defect in the software they were using. I noticed with some interest that there was an article in Nature about 6 to 7 months ago where Nature had to withdraw a half a dozen scientific papers because the results that were published in those papers were incorrect because of software defects. And there was an editorial article in Nature that maybe computational scientists should pay more importance to software engineering methodologies to avoid these embarrassments of producing incorrect results into the scientific literature because of programming errors. It's been sort of a vindication of mine saying that software quality is important. But when I spoke with the supercomputer center directors, I just asked them one question, and that is, what's your quality plan for your software? I didn't meet a single supercomputer center director who understood what my question meant, because their idea of software engineering methodology for producing scientific software at that time was you pick up a dusty deck from the shelf, the computational scientist gets a graduate student to hack up the deck to then solve the latest equations that the scientists had come up with. And there was no rigorous process involved in making sure that the software did what it was supposed to do. So software quality is particularly important in these mission-critical applications of software systems. I think it's equally as important for the scientific enterprise just to make sure that the results that we publish that depend on software are accurate. And there's been a lot of debate in the scientific research community of how do we ensure this. As you're also well aware that there are now some mathematical proofs that have been done with the use of software. And the mathematics research community doesn't really know how to verify that the software that's being used is correct. So what does this say about the mathematical proof? It's not a proof in the traditional sense of mathematics. So some very significant issues, both on the scientific front and on the safety front, and also on just well-being to society, of making sure that we know how to produce robust software and be able to give some certification that the software does what we think it's doing.
You were involved in some of the early research in the core of computer science, the foundations, the kind of things that are now in textbooks. As this has matured, what are the next frontiers?
Computer science is poised, or could be poised, to have even more impact on the world at large than it has up to this point. I think the impact can be best achieved, though, through interdisciplinary work. So one of the areas that I'm not doing research in, but I'm fascinated by, is how does the human brain work? What kinds of algorithms and data structures does the human brain use to process information? There are some centuries-old, maybe millennia-old questions that philosophers have asked. What is consciousness? Where does consciousness come from? If the human brain is just a computer, does this mean that we could program a computer to have human-like qualities like consciousness? Now, I was reading a book by Christoph Koch on the quest for consciousness. He's a famous neurobiologist. And reading the book, I discovered that the neurobiologists really don't understand consciousness at all. They don't even have a good definition for the term consciousness. But here are questions that have been with humankind ever since humankind began thinking about philosophy, that computer science perhaps could shed some knowledge on. but I don't know that I'll live long enough to see the fruits of this area of research. But on the other hand, we're making enormous progress in applying computer science ideas, computer science algorithms to areas like genomics, doing sequence alignment. Computer programs are able to do computer systems that use software can do sequence alignments, genomic analyses much more cheaply than before. What happens if we are able to, as part of our medical exam, to get a genomic analysis as well as a blood test to say what our current condition is? And this raises also some very interesting philosophical and ethical questions that, do I really want to know what is in my genes and what's in store for me, or what are the genes going to inflict on me in my old age? But I think these kinds of questions become approachable through the use of algorithms, computer science techniques, data mining techniques, but most importantly, it's going to be a collaboration with biologists. If we look at other areas of interdisciplinary studies, let's take quantum computing. The abstractions that a quantum computer enshrines are very different from the kinds of abstractions that a classical computer, a von Neumann computer, enshrines. We really don't have the programming techniques that well understood for how we can harness the power of quantum mechanics and quantum phenomena in computation. Shor, who was a mathematician at Bell Labs when he came up with his famous algorithm for being able to factor integers in polynomial time on a quantum computer, suggests that maybe it's possible to do certain computations on quantum computers more efficiently than we know how to do them on classical computers. But we really haven't come up with another blockbuster algorithm other than Shor's algorithm and Grover's algorithm for being able to do unfettered search in square root of n time rather than n time. So I think we still need to develop the abstractions and perhaps more importantly the programming languages and programming techniques to try to harness the power of quantum phenomena. But we can pick almost any area of human endeavor and say what happens to that field of study when we can apply computer technology to it. I think another interesting area for application is being able to do experiments in psychological research on a massive scale, that we can conduct psychological experiments over the internet involving hundreds of thousands of people, where previously, if we do it in a controlled lab session, it can only involve a much smaller number of people. So pick your field of human endeavor. We can develop, and there are techniques still to be developed for applying computer science ideas to it in a more effective fashion. So I think rather than seeing a retrenchment of computer science, we're going to see an explosion of computer science in conjunction with other areas of human endeavor.
Will the scientists, biologists, physicists have to learn more of computer science? And will computer scientists have to learn more of biology, physics?
I think the short answer to that question is yes. If we take, say, quantum computing, an area that I'm a little bit familiar with, to effectively harness quantum phenomena and build quantum computers requires more than just physics per se, more than just mathematics per se, more than just computer science per se, more than just electrical engineering per se. It's going to require a multidisciplinary effort. I had a fascinating interaction with Ike Chung at MIT. He's one of the premier people in quantum computing in the world. I had a graduate student, and she spent a year in Ike Chung's lab at MIT, because if you're in the compiler arena, it's important not only to know the source language, but also to understand the target machine. And Ike Chung was the first person to have implemented Shor's algorithm on an NMR machine. He had a chemist build a 7-atom molecule when he was at IBM, and with those 7 molecules, each supporting a qubit, he was able to implement Shor's algorithm to factor 15. It was a tour de force, but it showed that Shor's algorithm works and could be harnessed. Now, the big quest in quantum computing, the physicists have to come up with many more coherent qubits. The algorithms and computer science community has to be able to develop more effective algorithms and computing tools to be able to program those machines. We also need to develop computer-aided design tools. Today, there's a multi-billion-dollar industry that's involved in building tools for constructing classical computers. We are probably going to need at least as much software to build the quantum computers of the future. If you really want to work in quantum computing, you need to understand quantum mechanics. You need to understand mathematics of several kinds, complex linear algebra. You should know what complex Hilbert spaces are. It helps to know number theory. And there is a new style of quantum computing that's being investigated called topological quantum computing, where to construct a topological quantum computing, one can take a slab of very pure gallium arsenide, put on top of it a slab of gallium aluminum arsenide, put it into a refrigerator, chill it to a few millikelvin, put it into an intense magnetic field, and then in the interface, the electrons form a new state of matter where they evince the fractional quantum Hall effect that, amongst Horst Stormer, who was at Bell Labs, was one of the co-discoverers of this and for which he won the Nobel Prize. So it has this very interesting phenomenon that in this new state of matter, these quasi-particles emerge out of the quantum vacuum. You can put a probe on top of one of the quasi-particles and rotate it 360 degrees around another quasi-particle, and that somehow or another computes a unitary transform. This has more robust error tolerance than classical quantum computing technology like ion trap machines. So here is a new technology that's coming on stream, but how do we then construct the algorithms to do algorithms in this new setting? Programming the topological quantum computers becomes a job for topology. We're computing braids in space-time. So it's an ordinary computer science undergraduate program doesn't equip a computer scientist to study all of the disciplines required to understand this. Likewise for physics or for electrical engineering or even for mathematics. So what I think it requires are people who can know enough to know what they don't know, and then to be able to very quickly learn some of these new disciplines. So this is a challenge, I think, for education in the future, and also I think for doing science in the future, that we're now looking not just for long, skinny men and women who understand a given technology at depth, but some people like Bill Wolf, when he was president of the NAE, looked pie-shaped men, with the Greek letter pi, where you have depth in more than one area of science, and then a bridge to be able to connect them. I don't know where to find these kinds of people. And so maybe that's also another part of the educational process, is to try to attract people to the field who are capable of doing this kind of research.
The time that you don't do research, I know some of that time you spent playing music, and I know there are other people in the field also. Can you talk about the role of music in your personal life, and what does it contribute?
I had some wonderful interactions with Don Knuth at Stanford when I was on sabbatical at Stanford through music. I had brought my violin with me, and when Don heard that I played the violin, he had invited me to come and play some violin and piano sonatas with him. Now, Don is a very talented amateur musician, but we had some wonderful musical evenings, and before the musical evenings, we'd often have dinner and talk about computer science, interesting word problems. He also made the observation that many mathematicians and computer scientists not only were good at mathematics or computer science, but they were also good at music. He himself was a good example of this, and he had a number of other examples of other mathematicians and computer scientists who were very talented in music. I understand that much of the faculty at MIT plays the violin or some other musical instrument. So maybe your neurons, if they're wired up to be good at science, they might also be wired up to be good at music. I know we have some faculty members at Columbia whose undergraduate degree is in music. So this might make for an interesting experiment to see, does music facilitate computer science, or does computer science facilitate your musical talents? But it's interesting that there is this kinship between music and computer scientists and mathematicians. I've also, I've been playing the violin from a very early age. I went to a very musical high school in Toronto where I played in their orchestra. This orchestra had a wonderful music director, and there used to be a music competition in Toronto called the Kiwanis Festival. Our orchestra would win the Kiwanis competition year after year, and frequently our orchestra would go on tour to other high schools in the province of Ontario to show off what a musical program at a high school could do. The senior orchestra had a better reputation within the student body than the senior football team, because the senior football team, I don't think, ever won as many championships as the senior orchestra did. But through the playing in the orchestra, the young woman who was the concert mistress of the orchestra, I played beside her. She went on to play with the Toronto Symphony. And whenever the Toronto Symphony comes to play at Carnegie Hall, I usually try to get her to come and play with our string quartet. So it's a heady experience playing with professional musicians, because they're just so talented in the field. So I've found music to be extremely relaxing, and also I have written books and papers in computer science, but when I play the string quartets of Brahms, Beethoven, Mozart, I just wonder to myself of how were their brains wired up? How could they compose this divine music? I could never, ever emulate anything that they have composed. So I think what it suggests is that the human brain gets wired up in many different ways, and perhaps it requires a very special kind of wiring to be world class in no matter what you do. But maybe being exposed to the field when you're very young is extremely important, and that may also suggest that it would be very important for the field to get not only computer science into the high schools, but also into the elementary schools, so that students can develop the neural wiring to make great contributions to the field.
During your career, have you been involved with patents, and what was your experience with them?
Software patents are a very interesting question. When I was at Bell Labs, patents were very important to Bell Labs. There was a lot of software that was being created at Bell Labs. And the patent attorneys at Bell Labs were exploring the question of, can software be patented? So I was involved in some of the very early discussions of software patents with the AT&T attorneys. In the early days, if you came up with a new algorithm, since only hardware could be patented, or they thought that everything had to be reduced to a hardware, we had to construct hardware circuits to implement our algorithms, and these then could be patented. But then, after a while, there was some relaxation on patents didn't have to be physically realized. You had to just describe how they could be realized. There was also a discussion of what's the relationship between software patents and mathematics patents. And there was a rule saying that mathematics is not patentable, but processes are. Out of all of this, though, software patents became very important to industry. AT&T aggressively pursued software patents. I remember talking to a patent attorney who had visited Microsoft to talk about enforcement of some of AT&T's software patents, and the patent attorney was not admitted into Microsoft, saying, we're not interested in software patents. Today, Microsoft is one of the most formidable patenters of software, and as you're well aware, the industry as a whole is very much concerned with software patents, and there have been multi-million-dollar litigation suits launched by one company versus another in terms of patent infringement. There are several issues that I see associated with software patents. In the early days, there were investigations, or the patent attorneys would come and ask me, well, I have somebody who claims to have patented Gaussian elimination, and since we're a user of Excel or a spreadsheet, and the spreadsheet uses Gaussian elimination, they're claiming that we owe them damages. So the whole issue of prior art becomes a very important discussion, and one of the centering forces for patents is that it should be new, useful, and non-obvious. Well, Gaussian elimination was hardly new. Probably at the time it was invented. It was non-obvious, but it's certainly useful. So I think there still needs to be a shakeout in terms of software patents to avoid the frivolous nature of some of the software patents. But on the other hand, companies invest a lot of money in developing software, developing algorithms, so they deserve a return on their investment for creating these new algorithms. There's also a related issue of performance. You go and watch, say, the New York City Ballet put on a ballet. This gets into the issue of copyright. You can't go in and photograph the ballet performance and then go out and sell it because you don't have the intellectual property rights to be able to do this. So there are some issues also involved if you take a copyrighted source. We're now talking about copyright rather than just patents. If you take a copyrighted document and you want to transmit it over the internet, it gets performed, if you like, at each of the routers going across the internet. So are they violating copyright infringement? So I think some of the laws concerning software, both patents and copyright, were revisited and also may need to be revisited again as the technology changes. There's also the Digital Millennium Copyright Act, which changed some of the nature of what is copyright and what could be protected under this. I think you really need an attorney to talk about these issues. I have only been involved with some of these peripherally in terms of expert witness work, but for the would-be entrepreneurs, perhaps there should be more education in terms of the role of both patents and copyrights in terms of how successfully can you launch a business in a given area. As on a more personal front, when I was at Bell Labs, one of the more interesting patents that I got my name on was shopping in virtual reality. So the idea was that you'd be bicycling down the Champs-Élysées in virtual reality, and you come to a store, you go into the store in your bicycle, and you can shop. One of the claims of the patents seems to cover that. Whether it ever gets held up in court is another matter, but usually, at least Bell Labs' attitude at that time with regard to patents was that they would use it as a trading vehicle to be able to cross-license their patents with IBM or the other companies in the field. But some companies are now discovering that patents are valuable, and they may want to try to monetize their patents separately from cross-licensing agreements. It's a facet of computer science and the software part of computer science that we probably don't spend as much time talking about in the educational curriculum as we should, but it's a fact of the business world that needs to be considered.
Right, yeah. Companies buy other companies for their patent portfolio.
Yes, that's exactly right. There are several big name transactions of that nature that have recently occurred.
Has it impeded in any way the science or the issue of patents, or it hasn't really played any role in that? Or has it helped or impeded?
Well, I guess the original purpose of patents was to encourage publication. So patents are a form of publication. In engineering, if you have a long list of patents, sometimes that's beneficial to your career. Even universities love profitable patents. because the universities get license revenue from it. So Columbia, for example, gets revenues from the MPEG patent. So it can be useful from the point of view of bringing in additional money to support the research enterprise at universities. So that would be the good side of it. But on the other hand, I don't think the goal of scientific research should be to maximize your patent revenue. But maybe I'm just too old-fashioned on that front.